Hello everyone, welcome to my Additional Maths channel. For today's video lesson, I will share with you one of the hot questions from differentiation or derivative. This is a very interesting topic. I do hope that you will enjoy the video lesson. Have fun!
A 5-foot ladder is leaning against the wall. If the base of the ladder slides away from the wall at a rate of 2 feet per second, how fast is the top of the ladder sliding down the wall when the base of the ladder is 4 feet from the wall? So let me show you how to use our problem-solving strategy here to help us tackle any related rate problem easily. So let's go. First step, if possible, draw a diagram to help us visualize the problem. So a simple diagram for this question will look something like this. Right? So we've got a ladder leaning against a wall. So let's read the question again and start putting down information on our diagram. Let's go. So we've got a 5-foot ladder. So the length of the ladder is 5 feet. Okay, now, if the base of the ladder slides away from the wall at a rate of 2 feet per second, so if the base of the ladder right here slides away from the wall at a rate of 2 feet per second. Guys, look, if the base of the ladder slides away from the wall, some quantity is gonna change, right? If the base of the ladder slides away from the wall, some quantity is gonna change. What quantity? Would you say that would be the distance? That would be the distance from the base of the ladder to the wall, right? The distance here will change as the base of the ladder slides away from the wall, right? So in fact, as the base of the ladder slides away from the wall, the length of the segment here will increase, right? So that's why at this point, let me add one more variable to our diagram here. I'm gonna call that variable x. Okay, so I'm gonna let x be the distance from the base of the ladder to the wall. From the base of the ladder to the wall, right? Now, let's keep going. How fast is the top of the ladder? So top of the ladder is right here, right? So how fast is the top of the ladder sliding down the wall when the base of the ladder is 4 feet from the wall? So how fast is the top of the ladder sliding down the wall? Guys, as the top of the ladder slides down the wall, what quantity is going to change this time? Would you say the distance between the top of the ladder to the ground will change? In fact, as the top of the ladder slides down, the distance between the top of the ladder and the ground will what? Will decrease, right? Will decrease. So that's why at this point, let me add one more variable to our diagram to represent the distance between the top of the ladder and the ground, right? So we'll let y be the distance from the top of the ladder, to what? From the top of the ladder to the ground, right? To the ground. And now let's try to understand the logic behind this question here. Look. So say I have a ladder leaning against a wall, okay? Now look. As the bottom of the ladder slides away from the wall. So here's the wall. The bottom of the ladder is going to slide away from the wall. So as the bottom of the ladder slides away from the wall, look at the top of the ladder. The top of the ladder actually what? Slides down the wall. Right? Can you see that? Okay, now I'm going to do one more time. I want you to focus on the top of the ladder right here, okay? And now I'm going to what? I'm going to slowly pull the base of the ladder away from the wall. Okay, and then just focus on the top of the ladder right here. You see that? The top of the ladder slides down the wall, right? As the base of the ladder being pulled away from the wall. Okay? Yeah. So now, so that was first step. We just drew a very simple diagram to help us visualize the problem. And with the diagram, we can start putting down important information on the diagram, right? Yeah. Okay, cool. Now, moving on to step number 2. We want to express the given rates. Okay, we want to look for rates given by the question. Okay, now, what's rate? What's rate? Well, rate is defined as change in some sort of quantity over the change in what? This is important. Rate is always asking about how fast, how slow, right? Fast, slow, then we're dealing with what? Time, right? So that's why for rate, the denominator is always time. Okay? So let's look for any rate given by the question, with a unit having time in the denominator. Okay, so let's look for a unit with a time in the denominator. That will be right here, right? Do you see that? Feet per second. See? Feet per second. See, now look. At the denominator we have time in this unit, right? In this case, the time is measured in second, right? And anytime we have time in the denominator, we know we are given a rate, right? Yeah, okay? Now, so now we know the time is measured in second. Now, for this rate, what quantity is changing? Because at the numerator, we have to identify a change in quantity, right? So what quantity is changing? So now, look. If the base of the ladder slides away from the wall, if the base of the ladder slides away from the wall, would you say the length of the x segment is changing? Right? Look, let me show you. Guys, now look, okay? Let's say initially, the position of the ladder is like this, okay? So initially, what's x? Well, x is defined as what? X is defined as the distance from the base of the ladder to the wall. So x is defined as the distance from the base of the ladder, which is right here, to what? To the wall, which is right here, right? Yeah, so this is our x initially, right? When the ladder is positioned this way. Now look. As the base of the ladder slides away from the wall. So let's say the ladder is sitting on an icy ground, okay, very slippery. So now, as the base of the ladder slides away from the wall, right? So let's say the base of the ladder, get to here at some point in time. Okay, so if the base of as the base of the ladder slides away from the wall, see, now this is the new position for the ladder. Okay, so our ladder now looks like this. Looks like this. Right? So now it's like this, right? So so let's say as the base slides away from the wall, let's say get to this point. The base gets to this point. Now what's our new x? What's our new x for this position? See, if the ladder is in this position, what's the new x right now? Would you say the x now is still? X is defined as the distance from the base. So distance from the base from here to what? To the wall, right? To the wall here. See? X is always defined as the distance from the base right here to the wall. Right? So can you see that? So this is old. This is new. Right? See, the old x is only this long. The new x is now longer, right? So now, as the base slides away from the wall, that means what? What's being changed? And the change in quantity now is the change in what? The change in the length of x, right? The change of x. Okay, so this quantity is referring to the change in x. So change in the length of x, right? Now over change in time. In this case, time is measured in second, right? Now in calculus, change in is denoted as what? See, the triangle symbol means change, right? Change in. Now in calculus, the little triangle, change in, is denoted as d, right? Derivative or differentiate, right? So the change in is, in calculus, is denoted as d, right? So up at the numerator we have change in x. Now at the denominator we have the change in what? Time, right? So let's look at this again. Change in x dx over change in time over the change in time dt, right? Change in x dx, change in time dt, right? Yeah. Cool. So as it turns out, 2 feet per second. 2 feet per second is what? The change in x over the change in time. Can you see that? Yeah. Okay, so let me just write this out more nicely. So dx over dt in this case is 2 feet per second. Is 2 feet per second, right? Yeah. So this entire sentence here, if the base of the ladder slides away from the wall at a rate of 2 feet per second, this whole sentence is just telling us one information, dx dt. So dx dt is equal to 2 feet per second, right? And we should consider this unit as positive, right? We should consider this unit as positive. Why? Because let me ask you, as the base slides away, is x increasing or decreasing? X is increasing, right? So if the quantity is increasing, that means the change in quantity must be positive, right? So we should expect this guy to be positive. Okay? Yeah. Good. Now, so we're done with the second step. Okay, so just express the given information, the given rate, in the second step, we want to what? Express the given rate, right? So we want to look for the rate given by the question. We want to look for the rate, feet per second, given by the question. In this case, 2 feet per second is referring to what? Dx over dt, right? Cool. Now, let's move on to the third step. In the third step, we now want to express the asking rate. So in related rate question, the question always gives us the rate of one quantity and asks us to find the rate of another quantity. Right? So just see, like for this question, what's given by the question? The rate of x, right? Now, the question is gonna ask us to find the rate of another quantity. Okay, so we have to identify that. So let's identify the asking rate. Okay, so to look for the asking rate, we want to look for phrases such as how fast, asking about the rate, right? How fast, or at what rate, asking about the rate, or find the rate of what, right? Asking about rate. Okay, so let's look for phrases like this. How fast, at what rate, find the rate. Right here. How fast? Oh, how fast. So now the question is asking us to find the rate of some quantity. Okay? Yeah, so given. So now that's asking. So in the third step, let's express the asking rate. Right? So question is asking about how fast is the rate of what quantity. Now, how fast is the top of the ladder sliding down? How fast is the top of the ladder sliding down? Right? So that's asking about the rate of what quantity? Y, right? Because remember, y is defined as the distance from the top of the ladder to the ground. So right here. So in the initial position, while the ladder sits on the wall like this, now what's the y initially? Would you say the y initially would be what? From the top of the ladder to the ground. So this is our initial y, right? This is our initial y. Can you see that? From the top of the ladder to the ground. From the top of the ladder to the ground, let's define as y, right? Now look. As the top of the ladder slides down, say to this position right here. Now the top of the ladder is here. So what's our new y right now? Well, from the top of the ladder to the ground, that's our new y right now, right? So this is old, this is new, right? Yeah. So as the ladder slides down the wall, what quantity is changing? Y is changing, right? See, here's the old y, here's the new y. So y is changing, right? Yeah, so that's what the question is asking us. So the question is asking us the change in what? The change in y over the change in what? Time, right? Once again, rate. Bottom must always be time. Okay, guys? Yeah. So that's what the question is asking us. So how fast is the top of the ladder sliding down? So asking for dy dt, right? The change in y over change in time, right? The moment when the base of the ladder is 4 feet away from the wall, right? So the moment when the base of the ladder is 4 feet away from the wall, right? So the moment when what? The moment when the new x is equal to, whoops. The moment when what? When the new x is equal to 4, right? When the base of the ladder is 4 feet away from the ground. Does that make sense? So this is the moment when x equals 4. Does that make sense? Yeah, so now the question asking like this. Okay, let me do it one more time. As the base of the ladder slides away from the wall at a rate of 2 feet per second. So as the base right here of the ladder slides away from the wall at a rate of 2 feet per second. So dx dt is equal to 2 feet per second, right? Which is our given. Now, as the base slides away, the top of the ladder what? Slides down. Right? So now the question asks us, as the base slides away at a rate of 2 feet per second, and the moment when the base reaches a distance of 4 feet from the wall, how fast is the top of ladder sliding down? Right? So the moment when x is equal to 4, how fast is the top of ladder sliding down at that instant, at that moment? Okay? Does it make sense? So the question asks us, when x equals 4, what's the dy dt? What's the change in y over change in time? What's the dy dt at that moment? Okay? Yeah. Cool? Yes. Let me just erase the old. Cool? Yes. So step number 3, done. Moving on to now step number 4. We want to write an equation that relates the various quantities of the problem. So now let's look at this. What are the quantities in our problem here? Well, look. In our problem right here, see, as the ladder slides away from the wall, guys, I want you to look. So at this moment, I want you to look at this triangle. Can you see this triangle right here? I want you to look at this triangle. Right? In fact, let me draw it out. So guys, as the ladder slides away from the wall, okay, now let's say at this instant, when the base of the ladder reaches 4 meters away from the wall, okay, so at this instant, we have a triangle, right? Let's just focus on this triangle. Let's focus on this triangle. So we've got focus on this triangle. So this is our hypotenuse, and this is our x. Whoops. This is our x, and this is our y, right? So the moment when x is equal to 4, we've got a triangle that goes like this. Okay? Now we know this triangle doesn't just stay like that, right? Because, guys, look, because the base of the ladder constantly what? Constantly slides away from the constantly slides away from the wall, okay? Yeah. Now let's just take a snapshot for this moment, okay? So the moment, that split second, the moment when x is equal to 4, we've got this triangle here, right? So what quantities do we have here? So we have see, now let's look. In this triangle, we've got x right here, right? See, the horizontal distance here represents x, right? Right? And then the vertical distance for this triangle represents y, right? So in step number 4, we have to come up with an equation that relates the various quantities of the problem. Okay, so guys, can you come up with an equation that can somehow relate x and y in that one equation? Obviously, that equation in this case is going to be the triangle equation, right? The Pythagorean theorem, right? Because look. So that the relating equation, equation in this case will be what? Pythagorean theorem, right? Now, because looking at this triangle, how would you write out the Pythagorean equation? That would be what? That would be x squared plus y squared, x squared plus y squared is equal to what? The hypotenuse squared, right? And the hypotenuse is still, well, the length of the ladder doesn't change, right? The length of the ladder is always 5, right? It doesn't matter how the ladder slides. The length of the ladder always stays the same, right? So the length of the ladder stays at 5, right? So that is equal to 5. Oops. Five squared, right? See? By writing out the Pythagorean equation, x squared plus y squared is equal to the hypotenuse squared. So as you can see, the relating equation successfully relates the quantities x and y together. Next, we're going to come up with a way to somehow convert the relating equation into a new equation that involves rate, such as dx dt, dy dt. And that way, we can plug in the rate information into the new equation, right? So that leads us to step number 5. Step number 5, we're going to differentiate both sides of the equation with respect to time, because we're dealing with rate, right? So we have to perform derivative with respect to time, okay? And we're going to apply the chain rule again. See, anytime we perform derivative, we have to apply the chain rule, right? Okay, so at this point, I think it would be a good idea for us to do a quick review on chain rule. And when dealing with chain rule, I like to use a technique. It's called the bracket technique. So if you are not familiar with the bracket technique, I would strongly recommend you to, go on the search bar, type chain rule, and just take a look at how I deal with chain rule. Okay, it's very easy to understand. It's very effective. Okay, it's called bracket technique. So the derivative of bracket squared, derivative of any function squared is what? Well, first of all, we have to apply the power rule, right? So in applying the power rule, we bring the exponent to the front. So bring the 2 to the front, right here. And then what do we do next? Subtract 1 from the exponent, right? So subtract 1 from 2, we get 1. And here's the chain rule part, right? Here's the chain rule part, right? We're just going to take the derivative of whatever the function is inside the bracket. Okay, guys? Yeah. So now, let me give you a few examples. Let's say we want to take the derivative of the square root of sine function, sine x. So inside the bracket, I'm just going to put down the function sine x, okay? And just like that, we can find the derivative very easily. So the derivative of sine x, the whole thing squared, is 2 sine x, easy, right? Times, now what's the derivative of sine x? Derivative of sine x is cosine x, right? Then we're done, right? Cosine x, and we're done. Simple as that. See, really cool, right? Now, how about inside the function? How about the function inside the bracket now? If I put x, oh, that's even easier, right? So inside the bracket put x, inside the bracket put x. So the derivative of x squared is 2x times, now the derivative of x is just what? 1. Right? The derivative of x is 1. Another way you can look at this is just think of this as dx over dx, right? And if we have the same thing at the top and bottom, it cancel out to be 1, right? It's like this. 5 over 5 is 1. 50 over 50 is 1. So dx over dx is also 1, right? Yeah, so, and 2x times 1 is just 2x, right? So that's why the derivative of x squared is 2x. And usually this is a no-brainer, right? Usually you tend to think that, yeah, for something so easy, we don't have to apply the chain rule. I just want to make a point that chain rule is everywhere. The fact that you don't have to apply the chain rule is because here, right? Because while applying the chain rule, you just get 1. And multiplying by 1 doesn't change anything. Okay, but chain rule is still there though. Okay, now, how about if inside the bracket the function is y, then what do we have? So the derivative of y squared with respect to x is 2y times, and now this guy is just what? dy dx, right? It's just dy dx. Okay, or some people like to write this as, some people like to write dy dx as y prime, right? Yeah, simple as that. Okay, so that was performing derivative with respect to x. But in this section, related rates, we know the bottom, the denominator must be what? Time, right? But guess what? In applying the chain rule, we do the exact same thing. We perform the exact same procedure. The only difference is that if we are taking the derivative of a function with respect to time, guys, the chain rule portion right here must also be derivative with respect to time. Okay, just be careful there. Okay, now let's go. So let's say today, if inside the bracket, the function is a very simple function, just x. Okay, so inside every bracket, we just put x. So now what's the derivative of x squared with respect to time? Okay, easy. See, the bracket technique makes everything very easy. Okay, so derivative of x squared with respect to time is right here. Here we got 2x. Right. By the way, anything to the power 1 is just itself, right? So x to the power 1 is just x. Okay, now, how about the chain rule portion? So in the chain rule portion right here, what do we have? We just have dx over dt. Done. Just like that. Super easy. So the derivative of x squared with respect to time is 2x dx dt. Okay? Now, how about, what if we put it, what if we make the function inside the bracket as y? Same thing. Make it as y, same thing. Okay, so inside every bracket, let's just put y. So the derivative of y squared with respect to time is 2y times, right here, the chain rule portion is just dy dt. dy dt. And we're done. Super easy, right? Cool. So coming back to our question here. Yeah. So I think we are now ready to perform chain rule to differentiate both sides of the function. Okay? So let's apply chain rule. to differentiate both sides of the function. So we're gonna take the derivative of both, derivative with respect to time, right? Guys, rate. See, I was being careless there because I'm so used to writing d over dx. But no, guys, when we're dealing with rate, the denominator must be what? Time, right? Denominator must be time, so it's d dt. Okay, so now let's differentiate both sides of the equations with respect to time. Okay, now the left side of the equation, we just have what? X squared plus y squared, right? So x squared plus y squared. Now the right side of the equation, 5 squared is equal to 25, right? Yeah, can you see that? So you're just going to use chain rule to differentiate both sides of the relating equation, most important with respect to what? Time. And hopefully the new equation would involve rate, such as dx dt over or dy dt. Okay, so let's go. Yeah, so in this case, okay, we can just, on the left side of the equation, we can just what? Distribute the derivative operator into everybody inside the bracket, right? So d dt plus d dt, right? Yeah. So distribute the derivative operator into the first item inside the bracket, we get d dt of x squared, right? Distribute the derivative operator into the second item inside the bracket, we get d dt of y squared. Okay? Now, on the right side of the equation, guys, the derivative of any constant is 0, regardless of what the derivative is respect with, right? So taking the derivative of any constant with respect to time is 0, right? Derivative of any constant is 0. Okay, cool. Yeah. Cool. Now, and we talked about this earlier, right? See? The derivative of x squared, let's do this again, okay guys? Let's do this again. See here, what do you see? We're taking the derivative of x squared with respect to time. So inside the bracket, I'm just gonna put x squared, okay? So inside the bracket, I'm just gonna put down x squared. Oh, so sorry. So here we are taking the derivative of x squared with respect to time, right? So we're taking the derivative of x squared with respect to time. So basically inside the bracket, you can just put down x. So inside the bracket, put x, inside the bracket, put x. Right, so the derivative of x squared with respect to time is 2x times dx dt. dx dt, right? Yeah. So right here, derivative of x squared with respect to time is 2x times dx dt. Okay, guys? Yeah. Plus. Now, here we want to take the derivative of y squared with respect to time. Right? So we want to take the derivative of who squared? Y squared, right? With respect to time. So inside the bracket, we just put y. Inside the bracket, we just put y. So the derivative of y squared with respect to time is 2y times dy dt, right? dy dt. Okay? Yeah. So right here, the derivative of y squared with respect to time is 2y times dy dt is then equal to, the right side of the equation is just 0, right? And that's coming from taking the derivative of any constant with respect to time is 0, right? Okay, cool. Derivative of any constant is 0. Good, good, good. Now, and so we're done. So that, just like that, we successfully differentiated both sides of the equation with respect to time using the chain rule. Okay, and final step is easy. Now moving on to step number 6. Let me use another color. Moving on to step number 6. Moving on to step number 6, we just have to what? Substitute the given information into the differential equation and solve for the asking rate. Okay? Yeah. So I'm running out of space. Okay, let me bring this whole differential equation here. Okay? Let me bring it here. Okay, so the differential equation is 2x times dx dt, 2x times dx dt, plus, see, plus right here, right? Plus 2y times dy dt, plus 2y times dy dt is then equal to 0. All right, cool. So now we just have to what? Substitute the given information into the differential equation. So what's given? Well, this guy is given, right? dx dt is equal to 2. Right? You see that? Right here. dx dt is equal to 2. So dx dt right here is equal to 2. Yeah. So in the final step, it's a no-brainer. We just have to substitute all the given information into the differential equation. Okay? Yeah. And what else is given? Oh, right here. So what are we trying to find? We are trying to find dy dt, right? So this guy we don't know. This guy is what we're trying to find, dy dt. This guy we don't know. This guy we don't know, right? So this is the guy we're trying to look for, dy dt. But we want to solve the value for dy dt the moment when what? The moment when x is equal to 4. So the moment when x is equal to 4. Yeah? Guys, I think we're almost done, right? So now look. So we have, in the equation here, we have 2 in the front. Oh, oops. So in the equation here, in the differential equation here, we have 2 in the front, right? So we still need it. We have 2 in the front. And x is equal to 4. That comes from here, right? X is equal to 4. dx dt is equal to 2. dx dt is equal to 2 right here. Okay, well, I'm going to add plus 2. Okay, guys. We need to solve the differential equation for dy dt. We are still missing one information though. What's the y value right here? What's the y value right here? Okay, guys, once we find the corresponding y value right here, okay, then we're ready to solve the equation, right? Because we just have to make the equation equal to 0, right? So we're just missing one piece of information right here. What's the y value? Well, let's come back to our triangle right here. Guys, the moment when x is equal to 4, y is equal to what? Y is equal to what? Well, why don't we write out the Pythagorean theorem again? Let's write out the Pythagorean theorem again. Now look, okay? According to the Pythagorean theorem, x squared plus y squared is equal to what? 5 squared, right? That's the Pythagorean theorem for any right triangle, right? X squared plus y squared is equal to 5 squared, right? Guys, and guess what? We are trying to find dy dt the moment when x equals 4. So the moment when x equals 4, see, the moment when x equals 4, we can solve the Pythagorean equation to find y, right? To find the corresponding y value the moment when x is equal to 4, right? So this is plus y squared is equal to 5 squared is 25, right? Yeah, so let's solve this. So here we have 4 squared is 16 plus y squared is equal to 25, right? So solving for y here, so y squared is then equal to, so move 16 over, or another way you can think of it is subtract 16 from both sides of the equation, we get 9, right? We get 9. Okay? So solve for y, then y is equal to what? Plus minus square root of 9, which is plus minus 3, right? And since y refers to the length doesn't have negative, right? So in this case, y is just equal to 3. So the moment when x is equal to 4, y is equal to 3 in this little triangle right here, right? So the moment when x is equal to 4, the corresponding y value, this tells us the moment when x is equal to 4, the corresponding y value is equal to 3, right? And this is actually that famous triangle, right? Guys, next time we actually don't really need to solve it, right? When we have it, because there's a really famous right triangle that has a ratio of 3 to 4 to 5, right? The 3, 4, 5, right? Yeah. Right. So let's say if the length here is 30, the hypotenuse here is 50, then here must be what? 40, right? Yeah. This is famous one. 3, 4, 5. What's another famous one? Another famous one is 5, 12, and 13, right? Yeah. So this is the famous one. Okay? So 5, 4, then this must be what? 3. Okay, so anyways, so in this triangle, the moment when x is equal to 4, the corresponding y value is 3. So the corresponding y value right here is 3, right? Okay? Yeah. Good. So I think we are almost done. So let's solve the equation now. So here we have, so in the first term here, we have 2 times 4 is 8. 8 times 2 is 16. Plus the second term right here, 2 times 3 is 6. So we have 6 dy dt is then equal to 0. Right, so let's solve the differential equation here. So 6 dy dt is equal to negative 16. And dy dt is then equal to negative 16 over 6. Don't get too excited. I think we can simplify this we can simplify this fraction, right? Because both the numerator and the denominator are divisible by 2, right? So divided by 2 up top, we get a. Divided by 2 at the bottom, we get 3. Okay, so dy dt is then equal to negative a over 3. Negative a over 3. And that's our answer. dy dt is negative a over 3. Okay, and what's the unit? What's the unit, guys? Well, y is length, right? Y is length of the triangle right here, right? And length in this question is described as what? Feet, right? So y has a unit of feet. Over time in this case is what? Second, right? So dy dt is equal to negative a over 3 feet per second. And there's just one last note I want to point out, is that the fact that dy dt is negative means that the distance from the top of the ladder to the ground is decreasing, right? And that's why the change in y must be negative. Okay, so as the base of the ladder slides away, the top of ladder slides down, and that's why we should expect the answer to be negative. So to put the answer in a complete sentence, we will say that the moment when the base of the ladder is 4 feet away from the wall, okay? So the moment when the base of the ladder is 4 feet from the wall, is 4 feet from the wall, the top of the ladder, the ladder is what? Okay, sliding up or sliding down with a negative value. That tells us that the top of the ladder is sliding down. Is sliding down at a rate of a over 3. At a rate of a over 3 feet per second. At a rate of 8 over 3 feet per second. Let me just write here. Down at a rate of 8 over 3 feet per second. Guys, be careful, okay? When you write the final answer, make sure you don't add a negative sign right here, okay? Guys, we found the dy dt to be a negative value, which makes sense, right? However, when you write the final answer, the negative here simply tells us what? The top of the ladder is sliding up or down? It's sliding down. So guys, you already stated that. The top of the ladder is sliding down. So guys, you don't want to emphasize the same point twice, right? So it's sliding down at what speed? At a speed of, guys remember, don't put the negative sign. At a speed of 8 over 3 feet per second, okay?